Hi, my name is Robert Andrews, and I'll be speaking about the algebraic hardness versus randomness paradigm over fields of low characteristic. So as the title suggests, this is going to be a talk about de-randomizing some kind of algebraic problem, and we'll be doing this via the hardness versus randomness framework in a particular technical regime, which is captured by this low characteristic condition in the title. So to start, let's talk about the algebra. This is going to be a talk about algebraic circuits, which are a natural model for computing polynomials over a field. These are circuits whose input gates are labeled by formal variables, and whose internal gates are labeled by either addition or multiplication. We can also label the edges of this circuit by constants from our field, which has the effect of multiplying the value sent along that edge by the constant labeling it. These circuits then compute polynomials in the natural way. So for example, the circuit on this slide computes the polynomial x squared minus y squared. We measure the size of these circuits by the number of gates appearing in them, and we're going to view this computation in a syntactic manner. That is, our goal is to compute a polynomial as a formal sum of monomials. Now, there are a number of interesting questions one can ask about algebraic circuits. The one that we're going to focus on in this talk is going to be polynomial identity testing, which I'll abbreviate as PIT. This is an algorithmic problem in which I give you an algebraic circuit and I ask you to decide whether or not this circuit computes the zero polynomial. Now for this problem, I want you to think of the regime where the size of the circuit and the degree of the polynomial it computes are bounded by some polynomial function in the number of variables. It turns out there is an easy randomized algorithm for this problem. Namely, we just take the circuit and evaluate it at a randomly chosen point from a sufficiently large grid, and then we just check if this evaluation is zero or non-zero. And the correctness of this algorithm follows from the well-known Schwartz-Zippel lemma. Now, we have an efficient randomized algorithm for this problem, and one can ask if it is possible to design efficient deterministic algorithms for this problem. Unfortunately, we know of no non-trivial de-randomization for this problem. So it's an interesting question to design deterministic algorithms for PIT. However, if you've never seen this problem before, you might ask what utility there is in trying to find deterministic algorithms for it beyond the general task of de-randomization. And it turns out that PIT has a number of uses throughout theoretical computer science, two of which include the design of fast parallel algorithms for your favorite matching problem on graphs, and the design of efficient deterministic algorithms for primality testing. There are a large number of works concerned with de-randomizing PIT in various restricted settings, but in this talk, I want to focus on de-randomizing PIT for general circuits. And we're going to do this via the hardness versus randomness framework, which is this general paradigm that says we can de-randomize probabilistic computation under circuit lower bound assumptions. So, for PIT, this is going to specialize to the following form. We're going to start with a lower bound against an explicit family of polynomials. And from this, we're going to design an efficient deterministic algorithm for PIT. And I've drawn this arrow going in both directions because the connection does, in some sense, go both ways. But in this talk, we're going to be focusing on the conversion of hardness into pseudorandomness. Now, this is not a new idea or a new approach to de-randomizing PIT, so let me tell you what's known. So there are two flavors of result here, depending on what kind of field you're working over. If you know what it means, the results on this slide are going to hold when the characteristic of your field is 0 or large. And if you aren't familiar with that terminology, just think of these results as taking place over the complex numbers. The main result here is due to Cabanetz and Impagliazzo from the early 2000s, where they essentially proved the theorem that you want to prove. Namely, they showed how to de-randomize PIT under lower bounds assumptions. Quantitatively, they show that a superpolynomial lower bound yields a sub-exponential time algorithm for PIT, and an exponential lower bound yields a quasi-polynomial time algorithm. Now, this is pretty good, and nearly matches what we can do in the Boolean setting. But it's not clear if we can obtain a polynomial time algorithm for PIT under a hardness assumption. And indeed, this was an open question for about 15 years, until it was recently addressed in a work of Guo, Kumar, Saptharishi, and Solomon, who proved the following. they showed that you can obtain even better deterministic algorithms for PIT if instead you assume lower bounds against families of univariate polynomials. So here, we're going to have a family of polynomials, all of which are in one variable. And the parameter that we're going to care about is instead the degree of these polynomials, which we'll denote as d. This work showed that a lower bound, which is polynomial in the degree, suffices to obtain a polynomial time algorithm for PIT. Now, if you aren't familiar with this, you might ask, well, how do these univariate lower bounds assumptions compare to the multivariate ones? And the remark here is that it's not too hard to show that a univariate lower bound implies a multivariate lower bound. So in some sense, Guo, Kumar, Saptarishi, and Solomon are making what looks like a stronger lower bounds assumption and obtaining a stronger de-randomization. However, you can ask, well, is this truly a stronger lower bounds assumption, or is it equivalent to an exponential multivariate lower bound? And that is an open question of whether or not we can obtain univariate lower bounds from multivariate lower bounds. So at the beginning of this slide, I mentioned that these results depend on the field you're working over. And there's this word characteristic that's shown up twice now, so I better define it for you. So the characteristic is going to be some numerical parameter that's associated to the field we're working over. What is it? The characteristic of our field is going to be the smallest integer p, such that if I take the element 1 in the field and I add it to itself p times, I get back 0. And if there is no such p, then we're going to say our field has characteristic 0. So as an example, the rational numbers, the real numbers, and the complex numbers all have characteristic 0, whereas the finite fields all have positive characteristic. So somehow, these results are going to depend on the characteristic. Now in the previous slide, I alluded to the characteristic being large compared to the number of variables. What I mean by that is when we talk about 0 or high characteristic regime, what I mean is the characteristic is either 0 or it grows at least like some polynomial in n. And this exact rate of growth depends on what kind of theorem you're trying to prove, but usually it suffices to take the characteristic to be linear or quadratic in the number of variables. Conversely, what I'll refer to the low characteristic regime captures when the characteristic is a positive number, but it does not grow sufficiently fast for whatever your theorem is. And if you're not familiar with this sort of thing, or you're not used to thinking about it, for the rest of this talk, just think of p as being 2. This is kind of the most extreme end of the low characteristic regime. This is as low as your characteristic can get without actually being 0. So, what's known about the hardness versus randomness connection in the low characteristic regime? Again, the result here is due to the same work of Cabinets and Impagliazzo. And they, again, more or less prove the same theorem you want to prove, but the hardness assumption looks different. So what they proved is when the characteristic is small, you can de-randomize PIT, but now you need lower bounds against not just a family of multivariate polynomials, but in fact a lower bound against p powers of those polynomials, p squared powers of those polynomials, and so on. Quantitatively, this result looks exactly the same as the previous one, but I want to elaborate a little bit on what I mean by lower bounds against a polynomial and its p powers. So, in the regime of exponential hardness, this lower bounds assumption requires not just some polynomial f to be hard, but it in fact requires the p to the kth powers of f to be hard for k between 0 and some constant times n. So this is perhaps a somewhat strange lower bounds assumption where we ask for, in some sense, many correlated families of polynomials to all be sufficiently hard to compute. I should also mention that in the high characteristic setting, we saw that univariate lower bounds gave us stronger de-randomization. However, such a result is not known in the low characteristic regime. So we have some kind of hardness-randomness connection, but it would be really nice to remove this p-th power condition and somehow de-randomize PIT under lower bounds against a single family of polynomials. And that's what we're going to do in this work. So the theorem we prove is the following. We're going to show that in the low characteristic regime, we can de-randomize PIT from lower bounds against families of univariate polynomials. So we're trading this multivariate lower bound for a univariate lower bound, but we no longer require hardness of p-th powers. Quantitatively, we're going to more or less match what Cabanetz and Impagliazzo prove. That is, we're proving lower bounds here against degree d polynomials. So if we can prove a lower bound, which is super polylogarithmic in d, then we'll obtain a sub-exponential time algorithm. And on the other end, if we prove a lower bound which is polynomial in d, we can obtain a quasi-polynomial time deterministic algorithm. Now, how should you compare this to the previous work? Well, you should think of log d and n as being roughly equivalent here. And under this equivalence, you'll see that we're obtaining the same conversion of hardness into pseudorandomness. But there is this deficiency in that we require lower bounds against univariate families of polynomials as opposed to multivariate families, which is perhaps a more natural or more well-studied hardness assumption. The proof of this is roughly going to follow the same outline that Cabanetz and Impagliazzo took in their work, so it's no surprise that we're getting the same conversion of hardness into pseudorandomness. And in fact, the same result is going to hold if I replace these univariate lower bounds with lower bounds against a constant variate family of polynomials. And the same holds true for the work of Guo, Kumar, Saptharishi, and Solomon. So whenever I say the word univariate, you can replace it with constant variate and you'll get the same result, but I don't want to dwell on this too much. Now we did see in the high characteristic regime that these strong univariate lower bounds actually gave better de-randomizations of PIT. And you could ask the same question here, can we do that in the low characteristic setting? And the answer is, to some extent, yes. We also show that from a polynomial in D lower bound, we can obtain a de-randomized algorithm for PIT, which has running time, which is n to the 2 to the 2 to the log star n, where log star is this iterated logarithm. So the exponent on n here is certainly larger than a constant, but it's still a pretty slow growing number. So perhaps you can think of this as obtaining a quote-unquote near polynomial time algorithm for PIT, but it's not a genuine, gold standard polynomial time algorithm. And you might ask, where does such a strange running time come from? And essentially, we're going to use these bootstrapping results in the PIT literature, which were recently shown by Agrawal, Ghosh, and Saxena, and then subsequently by Kumar, Saptharishi, and Tengse. So this is the main result we're going to prove in this talk, and I want to take a step back and ask, why should we focus on this in the first place? And generally, when you're studying the complexity of these algebraic problems, you can ask yourself, does the characteristic of my field matter? And sometimes the answer to this question turns out to be yes. So for example, there are applications of PIT where the characteristic is required to be small. For example, there's a paper of Ryan Williams from 2009 that designs randomized algorithms for this k-path problem. And there, the application of PIT really requires the characteristic of the field to be 2. There are also instances where the characteristic matters where we're not talking about PIT. So for example, we know that sparse polynomials can have very non-sparse factors when the characteristic is positive. And we also know there are sparse polynomials with non-sparse factors in characteristic 0, but the separation is much larger when we're working in the positive characteristic setting. On the other hand, sometimes the answer to this question is no. So one of the main roadblocks to working in positive characteristic is the following. If you take the derivative of the polynomial x to the p, then this p comes out to the front, but in characteristic p is 0. So we end up having a non-constant polynomial whose derivative vanishes, and this might break your proof. But it turns out there's a notion of derivative that works better in this positive characteristic regime, known as a Haas derivative. And sometimes you can replace standard derivatives with Haas derivatives in your work and prove the same theorem in positive characteristic. So the point is, the characteristic sometimes matters for what we're trying to do, and sometimes it doesn't. And this talk is aimed at trying to understand this question of whether or not the characteristic matters in the context of this hardness versus randomness framework. So here's the theorem that we're going to try and prove. We're going to try and de-randomize PIT in the low characteristic regime using lower bounds against a family of univariate polynomials. So let me sketch the proof of this for you. So we're going to start by using the same framework that Cabanetz and Impagliazzo develop in their original work from 2004. And the main observation in that work is that one can reduce these questions of hardness versus randomness to questions about factoring algebraic circuits. Then we can use this work due to Kaltofen from the 80s, which says when the characteristic of the field is 0 or large, small circuits can efficiently be factored. And indeed, this is the approach that Cabanetson and Pagliazzo took in their original work. However, there's a catch. When we're working over a field whose characteristic is small, we may not entirely be able to factor circuits, but we can factor them up to taking a pth root. And what I mean by this is, suppose you want to factor a circuit and compute some polynomial f. Well, you may not be able to get a circuit which computes f, but you can definitely get a circuit which computes a pth power of f. So this is the main roadblock, and indeed this is the reason why the result of Cabanetson and Pagliazzo requires lower bounds against pth powers of polynomials. So how are we going to get around this? So we're going to prove a lemma that says when the number of variables is small, we can efficiently take roots, we can take pth roots of small circuits. And so this is going to get us over this technical hurdle that exists in small characteristic. And then, we're going to use some standard tools to transition between these univariate and multivariate regimes in the proof. And this is going to be the so-called Kronecker map, if you're familiar with this sort of thing. So for the rest of the talk, I want to zoom in on these last two bullet points. I want to talk about how we can efficiently take pth roots of small circuits, and I want to briefly describe to you how the univariate and multivariate regimes relate to one another. So the main contribution of this work really is about taking pth roots of circuits in characteristic P. And to set the stage for you, I want to draw your attention to a question which has been open since the work of Kaltofen on factoring circuits and indeed continues to remain open. Namely, if f to the p has a small circuit, does f itself have a small circuit? And in general, this question remains wide open, but our work will address this question in a particular regime of parameters, and indeed this will be a sufficiently interesting regime of parameters to do some kind of hardness versus randomness. So what we're going to prove is the following lemma. We'll show that you can take a pth root of an algebraic circuit and incur a blowup in size which is something like p to the n. Now, this is still pretty bad. We're incurring this exponential blowup in the size of our circuit to take a pth root. But we have the following easy corollary. Namely, when the number of variables is bounded by a constant, we can take a pth root and incur a blowup which is only some polynomial in the characteristic. And if you're thinking of the characteristic as being 2, this is saying that we can take a pth root, in fact a square root, and only blow up the size of our circuit by a small constant factor, which is more or less the best thing you could hope for in this area. So how are we going to prove this? There are going to be two ideas that go into the proof. So the first idea is that we're going to group the powers of x that appear by their remainder mod p. And then once we do this, we're going to apply a sort of gate simulation argument to convert our circuit that computes, say, f to the p into the circuit which computes f. So now I want to sketch what exactly I mean by this, and I want to do this over the field f2. I want to show you what this lemma looks like when we're working over f2 and say with just a univariate polynomial, because the ideas will readily generalize to a larger number of variables and to arbitrary characteristic. So suppose I have some univariate polynomial g, say this one. What I'm going to do is I'm going to take this polynomial and I'm going to group the powers of x by whether they're even or odd. So on the left, we have the powers of x which are even, and on the right, we have the powers of x which are odd. Now all the odd powers of x are divisible by x, so let's go ahead and factor that out. Okay, now we're going to use our key property of characteristic 2 here. Namely, in characteristic 2, the square of a plus b is the same thing as a squared plus b squared. So if you notice, in this third line here, we're writing g as the sum of, some polynomial, all of whose powers are even, plus x times a polynomial, all of whose powers are even. So if we have a polynomial whose powers are even, this a plus b squared equals a squared plus b squared, this is telling us that we can pull that square out. And so we can get the following representation for this polynomial g. It's a square plus x times another square. And so we're going to collapse this down, and we're going to call these two parts of g sub even and g sub odd. Okay, and so this is saying that we can write any univariate polynomial as the sum of a squared polynomial and x times another squared polynomial. Now, why is this useful? So remember, we're trying to take pth roots, and we're going to prove this in the special case when the characteristic is 2. So what we're really trying to do is we're trying to take a square root of a circuit. So if g is f squared, then we can compute f by computing the even part of g. So this is where this decomposition is going to be useful. Namely, if I have a circuit which computes, say, g, I'm going to try and transform it into a circuit which computes the even part of g. Okay, so now we've got this decomposition, so what are we going to do? So say I've got some part of my circuit where I've got a gate v with children u and w, and v is labeled by star, where star is either addition or multiplication. So what I'm going to do is I'm going to take these gates of my circuit, and I'm going to create for each original gate in my circuit 2 new gates, which are meant to compute the even and odd parts of those polynomials. So for example here, v in the original circuit computes some polynomial. And I'm going to ask that in this new circuit, v sub even and v sub odd compute the even and odd parts of that polynomial respectively. So now that we've got this idea, what we're going to do is we're going to sit down and stare at this decomposition for a little while, and we're going to observe that we can actually compute the even and odd parts of v using the even and odd parts of u and w. And then we're going to do this by building some gadget c star, which takes these even and odd parts of u and w as input and uses them to compute the even and odd parts of v. Now, the important thing here is that this gadget in the circuit actually has size bounded by a constant. So we can efficiently compute the even and odd parts of v from the even and odd parts of u and w. Now what we'll do is we'll take this construction, and given a circuit which computes f squared, we'll apply this construction to every gate in that circuit. So what this is doing is this is taking a circuit which computes f squared, and now we're computing all the even and odd parts of the gates appearing in that circuit. And if you think about this, what this does is this allows us to take the square root of the original circuit we were given by computing the even part of the output gate. Now I'm not going to describe exactly how you build these gadgets, but it's not too hard to figure out, and you just need to sit down and play with this decomposition for a little bit. But once you have this, you have this whole approach, you have the entire approach to computing pth roots. So that's how we're going to take pth roots of circuits. Let me tell you a little bit in the time I have remaining about multivariate and univariate hardness. Okay, so I mentioned on an earlier slide that univariate lower bounds imply multivariate lower bounds. And let me sketch the proof of this. So suppose I have some polynomial g, which is my hard univariate polynomial. What I'm going to do is I'm going to take this and I'm going to build a multilinear polynomial f on about log d variables so that this identity holds. And the way you should think about this is I'm taking each y term in g and I'm looking at its exponent and I'm sort of writing it in binary using these variables x that are appearing in f. Okay, and the reason you do this is this allows you to obtain a bijection between the monomials of g and the monomials of f. Okay, but that's not so important. What's really important here is if you look at this equation or you look at this identity, what this is really telling you is that if you have a circuit for f, then you can use this to compute g efficiently. Namely, you can bound the circuit size of g by the size of a circuit needed to compute f, plus some extra order n term to compute these powers of y. So if you flip this on its head, what this is saying is we can obtain a lower bound for f from a lower bound for g. And if you work out the details, this shows that a polynomial in D, lower bound for G, will yield an exponential lower bound for F. Okay, and this is going to be our main tool to translate between the multivariate and univariate regimes in our proof of this theorem. And I should mention that what's really going on here to some extent is that from our main lemma that we proved on taking pth roots, this is saying that not only is F inheriting the hardness of G, but in fact f to the p is inheriting the hardness of G, and f to the p squared is inheriting that hardness, and so on. And the way you can see this is, suppose I have a small circuit which computes f to the p. Well, then I can do this substitution and obtain a small circuit for G to the p. But then I can take a pth root, so I get a small circuit for G. So this is going to be the tool that we use throughout the work to translate between these multivariate and univariate regimes. So now I want to zoom back out and remind you one more time what it is that we prove in this work. So we're showing that you can de-randomize PIT in the low characteristic regime using lower bounds against families of univariate polynomials. And the approach here, the first two steps, are following the same framework that Cabinets and Impagliazzo use in their original work from 2004. But then we're going to make this extra observation that in the regime where the number of variables is bounded, we can efficiently take pth roots of circuits. And using that, plus this standard tool of the Kronecker map, we can obtain these hardness versus randomness trade-offs where we no longer need to assume lower bounds against pth powers of our hard family of polynomials. So this is the main theorem in this work. So let me just wrap up with the conclusion. So what do we do? So in this work, we instantiate the algebraic hardness versus randomness paradigm in the regime of low characteristic without this need for the hardness of pth powers of our hard family of polynomials. And the main observation that allows us to do this is this technique to efficiently compute pth roots of polynomials when the number of variables is small. Now, what are some problems that are left open by this work? Perhaps the main open problem here is to better understand the complexity of pth powers and pth roots. So as a concrete open problem, can we take a pth root and incur a blowup where the exponent on p is now sublinear in n? And already this would be interesting in the context of the hardness-randomness framework, in that this would allow us to start using multivariate hardness assumptions as opposed to these univariate or constant variate hardness assumptions in certain hardness regimes. The other problem, which is largely left open by this work, is to improve the de-randomization on the high end of hardness from this nearly polynomial running time down to an honest-to-goodness polynomial running time. Now, I should mention, our construction is based on the work of Cabinets and Impagliazzo, which is in turn some kind of algebraic analog of the Nissan-Wigderson generator. And the work of Gul, Kumar, Saptarishi, and Solomon in the characteristic zero setting uses a different construction. So it seems like perhaps in order to get a polynomial time de-randomization in the low characteristic setting, we may need some kind of new construction as opposed to just pushing these tools further. So that's all I wanted to say. Thanks for watching.